In propositional logic, a propositional formula is a type of syntactic formula which is well-formed and has a truth value. If the values of all variables in a propositional formula are given, it determines a unique truth value. A propositional formula may also be called a propositional expression, a sentence, or a sentential formula. A propositional formula is constructed from simple propositions, such as 5 is greater than 3, or propositional variables such as p and q, using connectives such as not, and, or, and implies. For example, implies. In mathematics, a propositional formula is often more briefly referred to as a proposition, but, more precisely, a propositional formula is not a proposition but a formal expression that denotes a proposition, a formal object under discussion. Just like an expression such as x plus y is not a value, but denotes a value. In some contexts, maintaining the distinction may be of importance. Propositions. For the purposes of the propositional calculus, propositions are considered to be either simple or compound. Compound propositions are considered to be linked by sentential connectives, some of the most common of which are and, or, if, then, neither, nor, is equivalent to. The linking semicolon and connective but are considered to be expressions of and. A sequence of discrete sentences are considered to be linked by and s. And formal analysis applies a recursive parenthesis rule with respect to sequences of simple propositions. For example, the assertion, "This cow is blue," "That horse is orange but this horse here is purple," is actually a compound proposition linked by and s. And "this horse here is purple." Simple propositions are declarative in nature, that is, they make assertions about the condition or nature of a particular object of sensation, e.g., "This cow is blue, there's a coyote." Thus the simple, primitive assertions must be about specific objects or specific states of mind. Each must have at least a subject, a verb, and perhaps an adjective or adverb. Dog probably implies "I see a dog," but should be rejected as too ambiguous. Example: "That purple dog is running," "This cow is blue," "Switch M31 is closed," "This cap is off," "Tomorrow is Friday." For the purposes of the propositional calculus, a compound proposition can usually be reworded into a series of simple sentences, although the result will probably sound stilted. Relationship between propositional and predicate formulas. The predicate calculus goes a step further than the propositional calculus to an analysis of the inner structure of propositions. It breaks a simple sentence down into two parts: its subject of discourse, and a predicate, a verb or, possibly verb clause that asserts a quality or attribute of the object. The predicate calculus then generalizes the subject-predicate form of symbols into a form with the following blank subject structure: underscore 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 predicate, and the predicate in turn generalized to all things with that property. Example: "This blue pig has wings" becomes two sentences in the propositional calculus. "This pig has wings," and "This pig is blue," whose internal structure is not considered. In contrast, in the predicate calculus, the first sentence breaks in two: "This pig" as the subject, and "has wings" as the predicate. Thus it asserts that object, this pig, is a member of the class of winged things. The second sentence asserts that object, this pig, has an attribute, blue, and thus is a member of the class of blue things. One might choose to write the two sentences connected with an as P, W and P, be the generalization of this pig to a member of two classes, winged things, and blue things, means that it has a truth relationship with both of these classes. In other words, given the domain of discourse, winged things, either we find P to be a member of this domain or not. Thus we have a relationship W between P and T, F. W evaluates to T, F. Likewise for B and P and T, F. B evaluates to T, F. So we now can analyze the connected assertions B and W for its overall truth value, i.e., and W evaluates to T, F. In particular, simple sentences that employ notions of all, some, a few, one of, etc. are treated by the predicate calculus. Along with the new function symbolism, F, two new symbols are introduced, and the predicate calculus, but not the propositional calculus, can establish the formal validity of the following statement. All blue pigs have wings, but some pigs have no wings, hence some pigs are not blue. Identity. Tashi asserts that the notion of identity lies outside the propositional calculus. However, he notes that if a logic is to be of use for mathematics and the sciences, it must contain a theory of identity. Some authors refer to predicate logic with identity to emphasize this extension. See more about this below. An algebra of propositions, the propositional calculus. An algebra, loosely defined, is a method by which a collection of symbols called variables together with some other symbols such as parentheses and some subset of symbols such as asterisk, plus, tilde, and v equals, are manipulated within a system of rules. Thus work inside the algebra becomes an exercise in obeying certain laws of the algebra syntax rather than in semantics of the symbols. The meanings are to be found outside the algebra. For a well-formed sequence of symbols in the algebra, a formula, to have some usefulness outside the algebra, the symbols are assigned meanings and, eventually, the variables are assigned values. Then by a series of rules the formula is evaluated. When the values are restricted to just two and applied to the notion of simple sentences linked by propositional connectives, this whole algebraic system of symbols and rules and evaluation methods is usually called the propositional calculus or the sentential calculus. While some of the familiar rules of arithmetic algebra continue to hold in the algebra of propositions, some do not. Usefulness of propositional formulas analysis. In deductive reasoning, philosophers, rhetoricians and mathematicians reduce arguments to formulas and then study them for correctness. For example, is the following argument sound? Given that consciousness is sufficient for an artificial intelligence and only conscious entities can pass the Turing test. Before we can conclude that a robot is an artificial intelligence, the robot must pass the Turing test. Engineers analyze the logic circuits they have designed using synthesis techniques and then apply various reduction and minimization techniques to simplify their designs. Synthesis. Engineers in particular synthesize propositional formulas from truth tables. For example, one might write down a truth table for how binary addition should behave given the addition of variables b and a and carry underscore in ci, and the results carry underscore out co and sum sigma. Example: in row 5 plus ci equals +1 equals the number 2. Written as a binary number, this is 102, where co equals 1 and sigma equals 0 is shown in the rightmost columns. Propositional variables. The simplest type of propositional formula is a propositional variable. Propositions that are simple, symbolic expressions are often denoted by variables named a, b, or a, b, etc. A propositional variable is intended to represent an atomic proposition, such as, it is Saturday, equals A, or, I only go to the movies on Monday, equals B. Truth value assignments. Formula evaluations. Evaluation of a propositional formula begins with assignment of a truth value to each variable. Because each variable represents a simple sentence, the truth values are being applied to the truth or falsity of these simple sentences. Truth values in rhetoric, philosophy and mathematics. The truth values are only two: truth T, falsity F. An empiricist puts all propositions into two broad classes: analytic, true no matter what, and synthetic, derived from experience and thereby susceptible to confirmation by third parties. Empiricists hold that, in general, to arrive at the truth value of a synthetic proposition, meanings must first be applied to the words, and then these meaning templates must be matched against whatever it is that is being asserted. For example, my utterance, "That cow is blue," is this statement a truth? Truly I said it. And maybe I am seeing a blue cow. Unless I am lying, my statement is a truth relative to the object of my perception. But is the blue cow really there? What do you see when you look out the same window? In order to proceed with a verification, you will need a prior notion of both cow and blue, and an ability to match the templates against the object of sensation. Truth values in engineering. Engineers try to avoid notions of truth and falsity that bedevil philosophers. But in the final analysis, engineers must trust their measuring instruments. In their quest for robustness, engineers prefer to pull known objects from a small library, objects that have well-defined, predictable behaviors even in large combinations. The fewest behaviors of a single object are 2, and these are put in correspondence with 0, 1. Such elements are called digital, those with a continuous range of behaviors are called analog. Whenever decisions must be made in an analog system, quite often an engineer will convert an analog behavior to digital by use of a comparator. Thus an assignment of meaning of the variables and the two value symbols, 0, 1, comes from outside the formula that represents the behavior of the compound object. An example is a garage door with 2 limit switches, one for up labeled SW_U and one for down labeled SW_D, and whatever else is in the door's circuitry. Inspection of the circuit might reveal that on the circuit board, node 22 goes to +0 volts when the contacts of switch SW_D are mechanically in contact and the door is in the down position, and node 29 goes to +0 volts when the door is 95% up and the contacts of switch SW_U are in mechanical contact. The engineer must define the meanings of these voltages and all possible combinations, including the bad ones. The circuit mindlessly responds to whatever voltages it experiences without any awareness of truth or falsehood, right or wrong, safe or dangerous. Propositional connectives. Arbitrary propositional formulas are built from propositional variables and other propositional formulas using propositional connectives. Examples of connectives include the unary negation connective. If is a formula, then is a formula. The classical binary connectives. Thus, for example, if and are formulas, so is. Other binary connectives, such as NAND, NOR, and XOR. The ternary connective if, then, else. Constant zero ARY connectives and the theory extension connective equals. Connectives of rhetoric, philosophy and mathematics. The following are the connectives common to rhetoric, philosophy and mathematics together with their truth tables. The symbols used will vary from author to author and between fields of endeavor. In general, the abbreviations T and F stand for the evaluations truth and falsity applied to the variables in the propositional formula. The connectives go by a number of different word usages, e.g., A implies B is also said, if A then B. Some of these are shown in the table. Engineering connectives in general. The engineering connectives are just the same as the mathematics connectives, excepting they tend to evaluate with 1 equals T and 0 equals F. This is done for the purposes of analysis, minimization and synthesis of formulas by use of the notion of minterms and kernel maps. Engineers also use the words logical product from Boole's notion and logical sum from Jevons' notion. Case connective. If, then, else. The if, then, else connective appears as the simplest form of case operator of recursion theory and computation theory and is the connective responsible for conditional gotos. From this one connective all other connectives can be constructed. Although, if C then B else sounds like an implication, it is, in its most reduced form, a switch that makes a decision and offers as outcome only one of two alternatives, A or B. The following three propositions are equivalent, and, V equals, or. Thus if, then, else, unlike implication, does not evaluate to an ambiguous truth when the first proposition is false, i.e., C equals F in. For example, most people would reject the following compound proposition as a nonsensical non sequitur because the second sentence is not connected in meaning to the first. Example: the proposition, if Winston Churchill was Chinese, then the sun rises in the east, evaluates as a truth given that Winston Churchill was Chinese, is a falsehood, and the sun rises in the east evaluates as a truth. In recognition of this problem, the sign of formal implication in the propositional calculus is called material implication to distinguish it from the everyday, intuitive implication. The use of the if, then, else construction avoids controversy because it offers a completely deterministic choice between two stated alternatives. It offers two objects, and it selects between them exhaustively and unambiguously. In the truth table below, D1 is the formula, and its fully reduced form D2 is the formula, or the two formulas are equivalent as shown by the columns equals D1 and equals D2. Electrical engineers call the fully reduced formula the and or select operator. The case operator is an extension of the same idea to impossible, but mutually exclusive outcomes. Electrical engineers call the case operator a multiplexer. Identity and evaluation. The first table of this section stars ******. The entry logical equivalence to note the fact that logical equivalence is not the same thing as identity. For example, most would agree that the assertion, "that cow is blue," is identical to the assertion, "that cow is blue." On the other hand, logical equivalence sometimes appears in speech as in this example. "The sun is shining" means, "I'm biking." Translated into a propositional formula, the words become, "If the sun is shining, then I'm biking," and "If I'm biking, then the sun is shining." If S, then B, and if B, then S, is written as an or in an abbreviated form as the rightmost symbol string is a definition for a new symbol. In terms of the symbols on the left, the use of the identity sign equals is appropriate, and equals different authors use different signs for logical equivalence. Typically, identity is written as the equals sign equals. One exception to this rule is found in Principia Mathematica. For more about the philosophy of the notion of identity, see Leibniz's law. As noted above, Tashi considers identity to lie outside the propositional calculus, but he asserts that without the notion, logic is insufficient for mathematics and the deductive sciences. In fact, the sign comes into the propositional calculus when a formula is to be evaluated. In some systems there are no truth tables, but rather just formal axioms, variables P1, P2, P3, and formula formation rules. The result of such a calculus will be another formula. Eventually, however, if one wants to use the calculus to study notions of validity and truth, one must add axioms that define the behavior of the symbols called the truth values, TF, relative to the other symbols. For example, Hamilton uses two symbols equals and when he defines the notion of evaluation V of any WFFS A and B in his formal statement calculus L. Evaluation V is a function from the WFFS of his system L to the range TF, given that each variable P1, P2, P3 in a WFF is assigned an arbitrary truth value TF. V equals F if and only if V equals T and V equals F. The two definitions and define the equivalent of the truth tables for the tilde and connectives of his system. The first one derives FT and TF. In other words, V does not mean V. Definition specifies the third row in the truth table, and the other three rows then come from an application of definition. in particular assigns the value f to the entire expression. The definitions also serve as formation rules that allow substitution of a value previously derived into a formula. Some formal systems specify these valuation axioms at the outset in the form of certain formulas such as the law of contradiction or laws of identity and nullity. The choice of which ones to use, together with laws such as commutation and distribution, is up to the system's designer as long as the set of axioms is complete.